All right, the moment you've all been waiting for. Well, the moment Andrew's been waiting for. Let's do some new material. I'm going to try and break things down into chunks as much as possible just to help manage your workload. I know you are probably getting slammed with AP review as everyone's trying to quick respond to things. So we still will progress, but I'm going to try it, keep it into bite-sized chunks as much as possible. So we started way back in chapter 1 with first order linear ordinary differential equations, ODEs. So they had some sort of a structure like this, and we talked about different ways of solving them. In 5.1, we looked at second order linear ordinary differential equations. And we looked at some different ways of solving those. That was the homework you hopefully have turned in now because it's past midnight on Tuesday morning. If we jumped to third order linear, we're just adding a third derivative in. And instead of P and Q, a lot of times they'll just use P and just add a subscript. And then that carries up, you could carry this as far as you want to go. Nth order would mean the highest derivative is to whatever the nth power is. And you can write your derivatives going all the way down. The principle of superposition for homogeneous equations deals with, we looked at a smaller version of this, but if you have y1, y2, y3, up to yn different solutions of the homogeneous linear equation from this slide, so looking at this differential equation, if C1, C2, C3, and Cn are constants, then you can take linear combinations of those solutions, and that will also be a solution. In 5.1, we just looked at C1y1 plus C2y2 and made that into a solution. This is the same idea, just carried out for more equations. So, for example, if y1 is e to the negative 3x, and y2 is cosine 2x, and y3 is sine 2x, and all of those are known to be solutions to this homogeneous equation. And we could do the work where we take and actually find the derivatives, first, second, and third derivatives in this case, of each of these and check that they are solutions. In this case, I hope you'll take my word for it, but you absolutely could do that as a side exercise, is find the three derivatives of each of these and confirm that they do satisfy this equation. If we wanted to write a general solution, all we would have to do is take C1, C2, and C3 times each of those solutions. And here they didn't give us any initial conditions. If we just had to write any two particular solutions, you could just fill in values for the constant. Now in this case, I literally just put in 5, 2, and negative 3. You could pick different constants. We normally don't just pick solutions. Normally what we do is they'll give you some initial conditions. Then you use the initial conditions and the derivatives to find them. But this first one is the general solution. Because it is not specified the constants. Both of these, if I can spell right, are particular solutions because they have values filled in for those constants. Okay, way back when in chapter 1, a particular solution for a first order linear differential equation was determined by one initial condition. All we needed was the value of y at some particular x value, and we could find the particular solution. In 5.1, we were working with second order linear differential equations, and there we needed two initial conditions. We needed an initial condition for y, and we also needed an initial condition for y prime. Well, if we expand and we have an nth order linear differential equation, I'm sure you'll never guess this, so we'll have to talk about this together, but that's going to require n initial conditions. Now, in order for a solution made up of linear combinations of all of these separate solutions to be able to satisfy a set of initial conditions, those solutions must be linearly independent. So, we need to talk a little bit about linear independence and linear dependence. First, linear dependence. The n functions, f1, f2, f3, up to however many n is, are linearly dependent on the interval I, provided that there exists some constants, c1 to cn, that are not all zero. Some of them could be zero, but that are not all zero, such that when you take c1, f1, f of x1, c2, f of x2. When you take the constant times those functions and you add them all up, they are linearly dependent if you can make 0 for some combination of constants. And this is similar to the way we define linearly dependent, our linear dependence with vectors. It's just instead of a constant times a vector, now we're talking about a constant times a function. And this is going to be our main task for today, is just showing linear dependence. So let's look at what the examples will look like. All right, so the 3 examples we're going to do that are going to be like the homework say, show that the given functions are linearly dependent for real numbers. And really what that means is we need to show that there is some constant that when you multiply times f of x, and another constant that when you multiply by g of x, and a third constant when you multiply by h of x, that we get 0. And the only rule is they can't all be 0. So I can't just do 0 times f plus 0 times d plus 0 times h. That doesn't prove that they are dependent. Now it does say show that they're dependent, so this should work for all of these. They're not asking are they independent or dependent. So in this first problem, we've got a bunch of polynomials. And so if I want to figure out a way to make it 0, what I would do is just start looking at the powers. So for instance, I only have 2 places where I have x squareds. So if I was going to try and get those to cancel out, quote unquote, you can't see me doing air quotes, but I promise that I am, I would need to take, or one way to do that would be if I took 4 times f, and I left h as just h. So 4f plus h. So if I do that, that means that right now I would be taking 4 times 4x squared plus 3. And then when I add the h on, I would have negative 16x squared minus 6x. And from here I would, 4 times 4x squared would give me 16x squared. When I take 16x squared and I subtract 16x squared, that would wipe itself out. Boom, I'd be done. The x squared terms would be gone. Okay, the problem is I'm going to have a 16x squared here, but I'm also going to have a 12. So I need to figure out a way to not only wipe out this 12, but over here I also have a minus 6. So that's where g comes into play. And when I look at g has a 3x and a minus 6. Well, if I am going to get this negative 6x wiped out, I'm going to need that times 2. Okay, well then let's try it and let's see what happens with the rest of this. If I take, 2 times g, that would be 2 times 3x minus 6. So then I'd have 6x minus 12 minus 16x squared minus 6x. And let's look at what happens. Well, here's my 16x squared minus 16x squared. That would give me 0x squared. Then I've got 6x minus 6x, so that's great. That's 0x. And I have 12 minus 12. Boom, we did it. So show that the functions are dependent. If I take 4f plus 2g plus h, I end up getting 0. I probably should have written that. Then, boom. All right, in this second one, I have 2e to the 3x, I have a negative 5e to the 3x, and then I have sine x. Well, let's start with the e to the 3x pieces. Right now, they don't have matching coefficients in front, or opposite coefficients in front, but if I took 5f plus 2g, 5f would end up giving me 5 times 2e to the 3x, which would be 10e to the 3x, and 2g would end up giving me 2 times negative 5e to the 3x, which would give me, oops, not equals, which would give me negative 10e to the 3x, and I'd be done, because they wipe each other out. So what do I do about h of x? Well, the only rule is I can't have all 3 of my constants be 0, but I can certainly have one of them be 0. And if I have 5f plus 2g plus 0h, I would end up with 0. So they are dependent, and that would be my combination of constants. All right, for the last one, let's get a little trig going on a Tuesday. Here I have sine squared x, and I have a 2 cosine squared x, and I've got a 12. Well, there is a property, or not property, there is an identity that says that sine squared x plus cosine squared x has to equal 1. So there's a couple of different ways that you could do this, but one is if I take g of x, if I leave that one alone, maybe I'll just write it as g. If I take g plus 1/2 h, that would end up giving me sine squared plus cosine squared x, which is going to give me 1. So then all I would have to do is wipe out a 1. Well, the easiest way to do that would be to take negative 1/12 of f. Negative 1/12 of f would end up giving me negative 1/12 times 12, which is negative 1, plus sine squared plus cosine squared. That gives me negative 1 plus 1, which is my 0. Now, you could do other things too. You could take 2g plus h, and then you would only do negative 1/6. So there's lots of different there's an infinite number of constants you could use for any of these, but as long as you can find one to show they're dependent, you are golden. And that's it. That's all we're going to do today. That's plenty.